Your crisper drawer is a slow-motion obituary for every vegetable you meant to eat. Pull it open right now and you already know what you'll find. The soft shoulder of a carrot going translucent, the skin of a potato pulling away from itself, a smell that's not quite rot but not quite fresh either. That drawer cost you $140 worth of produce last year. The USDA puts the average American household food waste figure at around 31% of purchased food, nearly a third of everything you buy, quietly decomposing inside a machine that runs on grid power, compressor coolant, and the assumption that none of that ever stops. The medieval English farmstead that fed 12 people through a 6-month winter didn't have a compressor. It had something older, smarter, and nearly free. And whatever they built, it worked, because those 12 people didn't starve. Here's the problem with your refrigerator that the appliance industry has never had any incentive to tell you. A modern fridge holds a steady 37 to 40 degrees Fahrenheit, but it does something far more destructive than most people realize. It desiccates. The refrigeration cycle pulls moisture out of the air to prevent ice buildup, which means it is simultaneously pulling moisture out of every vegetable sitting in it. The root vegetables, carrots, parsnips, turnips, beets, are between 85 and 90% water by composition. Put them in a machine designed to remove water from the air, and you are engineering their collapse from the inside out. Your appliance isn't preserving your food. It's slowly dehydrating it while charging you roughly $150 a year in electricity to do it. Modern refrigeration is a convenience masquerading as a solution. In the 1840s, American homesteaders building across the Ohio River Valley and the mid-Atlantic states weren't innovating when they dug their root cellars, they were inheriting. The practice had been carried forward from medieval English agricultural tradition, documented in estate records and farming almanacs dating to the 13th century. Where below-ground storage chambers were as standard a feature of a working farm as the barn itself. What those builders understood, without a single thermometer or soil science textbook, was that the earth itself was a refrigerator. A better one, a self-regulating one. And you can build it too. The science behind why it works comes down to 3 interlocking principles, and once you understand all 3, you will never look at the ground the same way again. The first is thermal mass, the capacity of a dense material to absorb heat slowly and release it slowly, resisting rapid temperature change. The soil has enormous thermal mass. Below about 4 feet of depth in most temperate climates, ground temperature stabilizes between 50 and 55 degrees Fahrenheit year-round, regardless of what the surface temperature is doing. That's cool enough to slow the enzymatic breakdown process inside vegetables, the internal chemistry that converts starches to sugars and eventually to mush, without crossing below the freezing threshold that ruptures cell walls. The second principle is relative humidity. Root vegetables require a storage environment between 90 and 95% relative humidity to remain firm and hydrated. Underground soil, when properly managed, naturally holds this range. The third principle is ethylene management. Ethylene is a colorless gas, a natural plant hormone, that ripening fruit and some vegetables emit as they age. In a sealed space, ethylene accelerates the ripening of everything else around it. A well-vented root cellar allows that gas to escape, which is why apples can be stored near carrots in a root cellar, but will destroy them in a sealed refrigerator drawer within a week. Think of it this way. A root cellar functions exactly like a ceramic slow cooker insert sitting inside a cast iron Dutch oven, not in terms of heat, but in terms of how mass holds a condition stable. The ceramic doesn't generate cold any more than the Dutch oven generates heat. What it does is resist change. It buffers. It absorbs outside fluctuation and refuses to transmit it inward fast enough to matter. The surrounding earth is your Dutch oven. The cellar chamber is your ceramic insert. What goes inside stays at the temperature and humidity the mass dictates, not the temperature outside, not the season, not the weather. The soil physics go deeper than temperature stability alone. Below the frost line, which in most of the continental United States sits between 12 and 36 inches depending on your region, the ground maintains a continuous vapor exchange with the surrounding earth through a process called capillary action, water molecules binding through surface tension and moving through microscopic soil pores toward drier zones. A root cellar with an earthen floor doesn't lose humidity. It sources it, drawing moisture upward from the water table at a rate calibrated to ambient conditions. This is why the USDA's National Center for Home Food Preservation specifically notes that earthen floor storage outperforms concrete floor storage for root vegetable humidity retention. Concrete seals the capillary connection. Dirt maintains it. There's also a microbial dimension most people overlook entirely. Healthy soil contains a complex ecosystem of bacteria and fungi, collectively called the soil microbiome, that actively suppress pathogenic organisms through competitive exclusion, meaning beneficial microbes crowd out harmful ones simply by occupying the same space first. A root cellar embedded in living soil is not just passively cool, it is actively defended. Before you break ground, understand what you are assembling. You need a site with a slope or a hillside where possible. A bank cellar built into a slope requires less excavation and allows gravity drainage to carry water away from the structure naturally. If your land is flat, you are digging a pit cellar, which requires a sump drain or gravel bed at the base. You need either fieldstone, dry-stacked concrete block, or rot-resistant timber like black locust or cedar for your walls. You need a ventilation system. 2 pipes, minimum 4 inches in diameter each, positioned to create cross-flow. You need a door rated to hold insulation value. More on that shortly. And you need basic hand tools, a spade, a post hole digger, a level, and a tamper. No power tools are required for a structure under 8 feet by 6 feet. Step 1 is excavation. Dig to a minimum depth of 7 feet below the surface. This ensures you clear the frost line in all but the coldest climates and puts your floor within the thermal stability band. Your footprint should be no smaller than 6 feet by 8 feet to allow air circulation around stored produce. As you dig, pile the displaced earth nearby. You will need it for backfill and for earthen berming over the roof. Step 2 is your floor and drainage layer. If you are on clay-heavy soil, lay 6 inches of coarse gravel at the base before tamping it level. This allows water infiltration without pooling. Do not seal the floor, but leave it as compacted earth or gravel. The capillary connection is part of the system. Step 3 is wall construction. Stack fieldstone or dry-laid concrete block to a height of 6 feet from the floor, leaving 2 4-inch circular openings near the top of opposite walls for your ventilation pipes. One pipe should be positioned low on the north-facing wall as a cold air intake. The other exits high on the south-facing wall as a warm air exhaust. As you work with stone, be aware that heavy stacked material requires a stable, level footing. Take your time with the base course, because an unlevel foundation will compromise the entire stack above it. Step 4 is roof and insulation. Lay rough-sawn timber joists across the top of your walls. 4-inch by 6-inch dimensional lumber works well for spans up to 8 feet. And cover them with planking, then a layer of 6mm polyethylene sheeting as a vapor barrier, then a minimum of 18 inches of compacted earth on top. And that earth layer is your primary insulator. Step 5 is the door. Face it north or northeast to minimize solar heat gain. Build a double door system, an outer wooden door and an inner insulated door with a minimum R value of 15, which you can achieve with 2 inches of rigid foam board sandwiched between plywood panels. The air gap between the 2 doors functions as a thermal buffer. Step 6 is humidity management. Install a simple hygrometer, a humidity gauge, inside the cellar. If humidity drops below 90%, place open buckets of damp sand or hang wet burlap near the intake vent. If it climbs above 95% and you notice condensation forming on produce, open the exhaust vent wider at night to encourage air exchange. The performance data on structures built to these specifications is not anecdotal. The National Sustainable Agriculture Information Service documents storage durations for properly cellared produce as follows. Carrots and parsnips, 4 to 6 months. Potatoes, 5 to 8 months. Winter squash, 3 to 6 months. Turnips and rutabagas, 4 to 5 months. Beets, 3 to 5 months. Cabbage, 3 to 4 months. And with optimal conditions and variety selection, some root crops remain viable for up to 24 months. The critical variable is entry condition. Vegetables must be cured before storage, meaning dried and cooled gradually to harden their skins and heal surface cuts. Damaged produce introduced into a cellar will spread rot. Sound produce introduced correctly will outlast your refrigerator's next compressor failure by a year. The cost comparison is direct. A standard root cellar of the dimensions described here, 6 by 8 by 7 feet deep, can be built with materials costing between $200 and $600, depending on whether you source stone locally or purchase block. It runs on zero electricity and requires zero coolant. A mid-range household refrigerator costs between $800 and $1,400 to purchase. Yeast consumes roughly 400 to 600 kilowatt hours per year in electricity, approximately $50 to $80 annually at average US rates, and has an average operational lifespan of 13 years before the compressor or control board fails. Over that same 13 years, your root cellar costs you nothing to operate and depreciates toward zero only if you neglect its drainage. The refrigerator depreciates toward landfill whether you maintain it or not. A woman named Seren, farming 4 acres in rural Pennsylvania, built a bank cellar into the north slope behind her barn in the spring of her first homesteading year. She spent $340 on materials, 3 weekends of labor, and finished before the first frost in October. The following April, 6 months later, she pulled carrots from that cellar that snapped clean and tasted of nothing but earth and sweetness. Her grocery spending on vegetables dropped by 60% that winter. She has not lost a root crop to refrigerator failure since. The food distribution network that restocks your grocery store operates on a 72-hour inventory window, 3 days of buffer between you and empty shelves. The electrical grid that runs your refrigerator is, by the Department of Energy's own reporting, increasingly vulnerable to weather events, aging infrastructure, and cascading failure. You already sense this. You have sensed it for a while. You can keep depending on a cold machine plugged into a fragile system. Or you can put your food preservation underground where no power outage, no supply chain disruption, and no appliance failure can reach it. The Earth was here before the grid. It will be here after it. Store what you grow or lose what you store. Your move.